Okay, when we look at this example, we can see that taking the integral of minus x on 5 minus x squared initially poses a problem because we've got x in the numerator and the denominator. Correcting that problem like we normally would in taking the term out of the denominator and trying to simplify won't work. And so we've got to come to another solution, which is to ask whether we think this might be the result of a product rule, which we can see it is. Now, actually, when I think about it, this method often comes up when we move into the calculus of trigonometry. So there are other times when we will see this situation. So thinking about, we want what we actually want. Well, it's quite easy, isn't it? Because we can see from the example above, it's exactly what we want. And so we'll know that it would go to the function 5 minus x squared to the half plus a constant, which could be written as the square root of 5 minus x squared. Okay, next one. The integral of 3x over root 5 minus x squared. Now, what do we see here, especially just following from that example, which you normally wouldn't have, but I can see that it's very close to what I want. I know that directly above it is what I prefer, because then that takes me to a very straightforward answer. What is the complication? The complication is there's a 3 and there is no negative. So we've got to deal with both of those. We want to be able to remove the 3 and we need to introduce a negative. Now, we know the only way of influencing what's going on within this integral is some product of 1, some way of writing 1. So I can see that I would like to remove a 3 by introducing a 3 into the denominator, and I want to also introduce a negative. So ideally if it was negative 3, and I'm multiplying by 3x over square root 5 minus x squared, then I can see that that would nicely cancel out and I would have a negative. However, I can't introduce 1 over negative 3. That is not positive 1. I can't introduce a negative 3. I can't just say, oh, well, let's put a 3 on the top. I can't do that either, because that is also negative 1. And a negative 1 will change a term. Multiplying by negative 1 definitely changes a term. The only number that doesn't change the situation is positive 1. So it means I have to introduce negative 3 on negative 3. Now, I might choose, and it's all going beautifully. The 3's cancel out. I've got, it doesn't matter which one of these negatives I keep. Let's say I keep that negative to sit here. Creates the situation exactly as I want it, a negative x over here. I'm left with this number out the front, which is a constant, which means I can actually take it out the front. And it is actually negative 1/3. I want to take out, well, I have to take out that negative. And, sorry, it's not negative 1/3. It's negative 3, isn't it? I've kept the third, so I'm wanting to take out the negative and the 3. So it's negative 3 times the integral now of negative x on square root 5 minus x squared. And we know that that will give negative 3 times y, times square root 5 minus x squared plus a constant. So it's unusual but you could be asked to integrate some product of functions without first having been given the derivative. And I guess you could be, it would be more common for that to happen in the extension exam. However, what is also common in the extension exam is the process for dealing with that situation, which is called the substitution method. But maybe, to be honest, maybe if the situation was something that you did recognise and you could avoid even the substitution method, then I would highly recommend you do it that way. The substitution method is a little bit complicated. It is unlikely in the advanced course, but I guess that doesn't mean that it couldn't happen. It is just something that you need to always have there and be part of your questioning, wondering process when you see a question. And like I said, normally if it's in extension 1, you'll have the added instruction to do it by substitution. So we'll try very quickly to get through these. 2 more examples. What can you see here and what do you know? We can see that we've got a product, and we normally don't integrate a product. Make sure you see this, think that. We normally don't integrate a product. Would we expand this all out, this cubic, and multiply by that? Probably not. Probably not. Though I suppose if you knew how to expand out that cubic, you could do that and distribute this and just get a nice long polynomial. And integrate each individual term. You could do that. Thinking then, if we're not going to do it that way, thinking, well, is this the derivative of what's inside? Well, we can see that the derivative of what is inside would actually be 3x squared. So is there any way that we can take the term that we have been given and write it in terms of 3x squared? Well, we can see, yes, we could. We would have an additional 4 to make up the 12. So if we were integrating that, we're very happy actually to see that 4, because we know now that the index would have been 1 more than that. So we go through almost our integration process where we go x cubed plus 1 to the power, add 1 to the index, normally divide by that new index. If we divide by that new index, the 4 would cancel out. And our 3x squared would cancel out, and so we nicely just get this plus a constant. Like I've said before, you can differentiate, bring the 4 to the front, x cubed plus 1 cubed times 3x squared would be the derivative, which 3 fourths of 12x squared, x cubed plus 1 all cubed is exactly that. So this is like our check. Differentiate the answer you get. It is what you're asked to integrate, so your answer must be correct. Now with this next one, what do we see? We see that we're being asked to integrate x in the numerator, x in the denominator. Automatically we say we don't have a rule for that. We've got to think about our options. Our options are, can we simplify it? Can we bring that out of the denominator and do some expanding and get something nice that we can integrate? And the answer to that is no, because when I bring that 5 out of the denominator, that 3, it becomes a negative 3, and we don't have any way of expanding our bracket with a negative 3. I think now about what happened when I differentiated something? What did the term look like that I differentiated to give me a -3? Keeping in mind that when you differentiate, you subtract 1 from the index. What must the index have been on the term such that when I differentiated it, I subtracted 1, I got a -3? I think you can see then, if I differentiate this bracket to a -2, bring the -2 to the front, and subtract 1 from the index, because that's the differentiation rule, subtract 1, -2 subtract 1 gives -3, I will still have to multiply by the derivative of what's inside my bracket, and I lost a squared there. So that's 10x, the derivative of that. And let's have a look at what we get when we simplify all of that. We get a -20x, negative index. At least we're getting the bracket to the power we want, and 5x squared minus 1 to the power 3. So you can see that when we do differentiate this 5x squared minus 1 to the -2, we end up with a negative, which is good. We want that, and I've ticked that, and the x term, and the denominator is perfect. The only term we end up with when we differentiate this that I can't see appearing here is a 20. That means something occurred here such that that 20 was eliminated. Well, we know that if you want to multiply by 20, you divide by 20. So that tells me that the original function that was differentiated to give me this must have had a 1 on 20 in it, and it was originally the function 5x squared minus 1 to the -2. And we could differentiate that. We could do our check, which would be this similar process to what I've done here. However, I would still have a 20 at the front, and a 20, another 20, and, a 1 on 20, a fraction 1 on 20, which would cancel out my 20 and give me what I was asked to integrate. You should be right to do 11H now.